Okay, so I would like to start today with kind of an open section answering questions you may have on a previous material. I think the way to go about this, I mean, in general, in mathematics, you should try to have kind of an airtight situation with the arguments, namely that you understand every step of reasoning. I mean, you want it to fly, so it needs to be either airtight or close to. I mean, you can have a little bit of leaked air, but too much you cannot fly. So I encourage you to go over the notes. It's they are supposed to be carefully written, so you should be able to follow every step. Of course, I could make some mistakes, or there could be some gaps, but if you see any, you should ask me, and then I'm happy to answer. Beside, you can also ask me to revise some section, so and that's also an option. But do you have any questions about previous material?
I do have one, which is related to the definition of fields and field homomorphisms. I remember that for field homomorphisms we discussed the sum and multiplication tables of them, so kind of simple equivalences. But can you give again the formal definition of what a field homomorphism is in an example, like just really briefly, like no?
That's it's actually very easy to revise. I mean, if we have let's say F and K, two fields. What does it mean to have a field? It means that I have a multiplication. In F, I would call it dot sub F, and addition that I would call plus sub F. And similarly, you have a multiplication in K and addition in K. And you also have the neutral element with respect to addition. This is the, let's say, 0F and 0K. And the neutral element with respect to multiplication. So this is 1. And okay, there are different axioms connecting. I mean, the multiplication and addition need to be associative, and there is also an axiom connecting multiplication with addition. This is called distributivity. It means that if you do A times B plus C, it's the same as AB times AC. Sorry, plus AC. And now, what is a field homomorphism? Which you can I mean, I typically call these things a field map. I mean, this kind of like an enveloping terminology that you can call. I mean, a group homomorphism is a group map. A field homomorphism is a field map. Ring homomorphism is a ring map, and so on. We will have more structures in the future, and for each of these structures, we want to have a notion of a map that is compatible with the structure. I mean, what is all you can think of all the notions we talk about as in the scheme of a certain data satisfying certain conditions. I mean, what is F? F is a set together with the data of binary operation, and I mean two binary operations and two special elements, 1 and 0, satisfying certain axioms. So it's like data plus conditions. And what you want in the notion of a map between these structures, I mean between two of instances of these structures, is something that is compatible with the data. I mean, so a field homomorphism is a function let's say F from big F to big K, such that I need to, again, to be compatible with the structure. It means that first I map 0 to 0. Then I need to map 1 to 1. And then I need to be compatible with the two binary operations. So for any A and B in F, if I do F of A plus B, it's the same as F of A plus F of B. And if I do F of A times B, it's the same as doing F of A times F of B. And notice I am being a little bit sloppy in notation, but this you should get used to. I mean, the plus here is the plus in F, and the plus here is the plus in K, right? Of course, it has to be because the input of the function F is the field, I mean, elements in the field F, and the output is elements in K. And the same goes for the multiplication. Yes.
So after seeing this, then of course, when there's a field homomorphism, it means that F and K, although might be the same, they aren't necessarily the same field, so they can be different fields. So can you put any simple example of different fields that are homomorphic to each other?
Homomorphic, you should distinguish homomorphism and isomorphism. Okay, that's a very important distinction. And again, this it pops out in basically all the structures we will consider. I mean, you have a group map, for example. I mean, you take integers to integers modulo n, you do the mod n. This is a group map, right? Because if you do a mod n and you sum it up with B mod n, it's the same as doing A plus B in Z and then do mod n.
Sure.
So this is a homomorphism, a group homomorphism, or a group map. I mean, it's compatible with the only operation. I mean, the only operation that I have in a group, which is just in this case addition or addition modulo n in the. These groups are not the same. You have a homomorphism, but they are not the same. In order for them to be the same, in the sense that we consider, you need to have an isomorphism, namely a group map or a group homomorphism that is both injective and surjective.
Okay.
And this you cannot possibly have a injective and surjective map between these two groups, because one is finite and one is infinite.
Sure.
So this is really, so you can think of it this way in groups, and again this will kind of be the same in fields. You take two groups, G and H. You have their, let's say there are a billion groups. So you have the addition table. I didn't say, I mean, you don't have to assume that they are finite, but let's just, for the example, let's assume they are finite. So you have some elements, I don't know, G1, G2, G3. And here you have the addition, I mean, whatever it is, G1 plus G2, and so on. And if you give me a group homomorphism, let's say F, then what I get, I mean, of course, I can simply write F of G1, F of G2, F of G3, right? And also here. Okay, now this is not a full list of the elements in H, because I did not assume that the homomorphism F is surjective, right? So possibly there could be other elements here, like I don't know, H1, H2, and so on. But for the elements that are obtained as an image of the function F, what I can say, because F is a homomorphism, is, I mean, here there should be F of G1 plus F of G1. But F of G1 plus F of G1, by the homomorphism property, it's F of G1 plus G1. Right, so I could actually write here F of G1 plus G1 if I know that the function F is a group homomorphism.
I see.
Okay, so a group homomorphism takes the addition table of G and copies it to some sub addition table of H. Now, if F was an isomorphism, it means that it's injective and surjective. Then I would really have, I mean, this list, F of G1, F of G2, F of G3, would be an exhaustive list of the elements in H, right? Because the map F is surjective, and there will be no repetition because the map F is injective. So you could really, if F is an isomorphism, you could really think of the addition table in H as simply a copy of the addition table of G with just different names of the elements.
I see. I see.
Okay? So this is why we say that isomorphic structures, I mean isomorphic groups, are the same, right? I mean, they're not the same as sets. They could be different sets. But if you, for instance, if you input it into a computer, the computer doesn't care. You know, you call it X or you call it Y, it doesn't matter. All that matters is the addition table. I mean, right?
Yeah. And
now the same goes for fields. I mean, if now I have two fields, again, they do not need to be finite, but in our case, we mostly deal with finite fields. So you have the addition table of F, and you have the multiplication table of F. And you have the addition table of of K. And you have the multiplication table of K. And a homomorphism is something that does something similar to what we had with groups, but for both the addition table of F and K and the multiplication tables of F and K. Right?
yeah.
Okay, and if you have an isomorphism between F and K, if this is an isomorphism, then I could really identify the addition table of F with the addition table of K, and the multiplication table of F with the multiplication table of K, up to a change of names. And the change of names is given by the map F, right? By this function F.
Makes sense.
Okay, so again, we will say that two isomorphic fields are are the same from the point of view of a computer.
So this clearly explains and cleared my doubt. Then this went to a place where I think this is related to the other question that I had. So I'll try to introduce it, which is from the standpoint of splitting fields. I went through the docs again, and I see the properties that we need such that we can have splitting fields. But is there any intuition behind having an anamorphism or isomorphic fields to the properties required to have splitting fields? In the sense of, do we require to explain splitting fields any intuition of these homomorphisms/isomorphisms to understand? I'm trying to just grasp a view of splitting fields that is just not an enumeration of properties, but rather some kind of geometrical point of view, to put it in some sense. I don't know how to say it.
Yeah, so let me start with the end. I mean, there's no geometry in splitting fields. I mean, at least not for now. A splitting field is an algebraic notion with no apparent geometric intuition, because, and especially in our case, we have finite fields. So it's very hard to, I mean, we will do some geometry of finite fields later on, but it needs to be understood in a different sense. And splitting field is an algebraic notion. Now, isomorphism and homomorphism, I mean, this is fundamental notion in any structure we will consider. So if you talk about fields, you will always consider, I mean, there will almost always be some kind of isomorphism of fields involved in the, either in the statement of the theorem or in the proof. It's almost impossible to avoid it. And the same goes for any of the other structures we consider. I mean, can you imagine that we would do dissection of groups without the notion of group isomorphism? It would be insane, right? And so of course, splitting fields, they also involve the notion of field isomorphism. And the deep reason is that actually splitting field it turns out to be a kind of field that is unique up to isomorphism of fields. So what happens? I mean, you start with the field F. It doesn't have to be a finite field, right? It's like most of the stuff we do on splitting fields are true for any fields. And you take a polynomial over this field, which is prime. You remember the definition of a prime polynomial?
Yeah, primitive polynomial. Yeah.
It means it cannot be decomposed into a non-trivial product of two polynomials. I mean, of course,
exactly.
it could be a product of a constant and another polynomial or something like that, but it cannot be a product of two polynomials of degree bigger than 0. Okay, so, and when we had this, I mean, okay, so in particular, phi has no roots in F, right? Because if it had a root, then you could write phi x equals x minus the root times some phi prime x. So then phi would not be a prime polynomial.
Yeah.
Okay, so a prime polynomial, you can be sure it has no roots. But now I would like to construct a bigger universe in which phi splits completely to linear factors, right?
Yes.
So if I could, I mean, I call this universe a splitting field. I mean, I would like to obtain a field that contains so I want some field K that contains F. And of course, if it contains F, then I can consider phi I can consider phi over the bigger field. I will still write phi, right? It's just it's basically the same polynomial, but now over K. And over K, we have a complete split of the polynomial phi. So I write it like this: alpha times product, let's say x minus alpha I equals say 1 to n. N is the degree of phi, where alpha and alpha 1 up to alpha n are now elements in the field K. Yeah.
You write alpha in front just because in case it's not a monomial, in case like the leading factor is not 1.
Yeah, exactly.
Okay, thanks.
It's called the monic.
Sorry, yeah, monic. Yeah.
Yeah. Okay, so I would like to, I mean, if I could, I would like to obtain a perfect universe, at least a perfect universe with respect to phi. I mean, it has all roots. And so one thing, I mean, eventually I would like to say this perfect universe, I mean, I would like it to be minimal as well, because I don't want to add too many stuff that I don't need. In this sense, I mean, this is the third property. If K prime is let's say, okay, let's call it L. If L is a field that on one hand sits between F and K, and on the other hand phi splits over L, then L must be equal to K. And you cannot do anything anything, I mean, smaller than than K. Yes. There was a
I
question?
think it was a question written in the chat.
Yes, I added a question on the chat. So, yeah, I was wondering, so if this extended field does not contain all the possible roots from the polynomial, does it mean that it's not considered a splitting field? Or it could still be a splitting field?
Yeah, a splitting field must contain all the roots, because I mean, you see this this formula in purple. It means, I mean, it means that alpha 1 up to alpha n are all the possible roots of phi.
Okay.
Right? Because first of all, I mean, there are certainly roots of phi, because if you substitute, instead of x, you substitute alpha I, then you get 0. And second, they must be all the roots of phi, because this is, I mean, how do I say it? If you have any other element, let's say beta, and beta is different, if beta is different than any of these guys, in fact, if it's only different than alpha 1 up to alpha n, you plug in beta into phi, you get something that is non-zero, right? Because, I mean, you get beta minus alpha 1, beta minus alpha 2, and so on. Each of these expressions is non-zero. In a field, you multiply non-zero elements, you get a non-zero element. So you cannot have any other root for phi. Yeah.
Are there any polynomials that, for some reason, you can't find the splitting field for?
No, we proved that a splitting field always exists.
Oh, okay.
Exist and unique up to isomorphism. So, okay, so let's do an example. I think I had like a good example in the notes. Okay, example. This you can find it.
Which is the number?
Yeah, it's like 557, I think.
Thank you.
So I start with the ground field. I start with Q. Okay, the rational numbers, and a phi of x is x to the 4. Let me call it f of x, just simpler. F of x is x to the 4 minus 2. Now x to the 4 minus 2 is prime over prime over Q. You can check it. I mean, there are different ways to check it. But for example, you cannot have. I mean, it's very easy to see that you cannot have any root of f over the rationals, because a root of f would be fourth root of 2, something like that, right? And fourth root of 2 is not a rational number. Just we showed that a square root of 2 is not a rational number, and you can in similar ways you can show that also fourth root of 2 is not rational. Okay, and of course also you could do minus fourth root of 2. This would also be, and in fact, if I think of Q as contained in the complex numbers, then I could figure out all the possible roots of f. This would be plus minus fourth root of 2, and plus minus I times fourth root of 2. Okay, and none of them belong to Q. So over Q, I cannot find any root. So now I consider K1, let's say. This is a Q x, I mean polynomials over Q, modulo the polynomial f. I mean, if you recall, we had this construction that you can consider all remainder polynomials. This set Qx modulo f. We also denoted it as a Qx sub f. This is kind of an analogous notation to Zn, right? And this is analogous notation to Z modulo Nz. Okay, but in terms of elements, this is all polynomials Rx, which are in our case, they must be of degree 3 or less. So it's like ak x to the k plus a1x plus a0, where the coefficients a0 up to ak are in the original field, I mean in Q, and k is strictly smaller than the degree of the polynomial we take modulo with. So in this case, k is smaller than 4. Okay, this is a set, right? And on this set, I have a binary operations. Let me write it slightly better. It's all the Rx, AK x to the K, A1 x A0, such that AI is in Q and K is strictly smaller than the degree of F, which is 4. Okay, and on this set K1, we have a modulo F arithmetic. I mean, I could do, if I have R1 and R2 in K1, then I could do R1 plus R2 modulo F. And I could also do R1 times R2 modulo F. In fact, if you think of it, when I do R1 plus R2, I don't need to do modulo F, because R1 and R2 are of degree smaller than the degree of F. And when you add two polynomials, you don't change the, I mean, the resulting degree is the maximum of the degrees. So it would still be a degree that is smaller than the degree of F, and therefore by the long division of polynomials, you don't have to do any operation to get the modulus, right? It's like in integers. If I do 3 modulo 5, it's still 3. But for multiplication, you do need to do modulo F. And these operations, what we showed, that because F is prime, and this is kind of analogous to, I mean, if you take integers modulo a prime, you suddenly get a field. I mean, you get a multiplicative inverse for every element. And so K1 is a field. Now, K1, of course, contains Q, because you can consider the constant polynomials. I mean, the ones with only a free coefficient x0. Okay, so now what we are guaranteed is that this is kind of an abstract construction, right? This QX modulo F. But we are guaranteed that there will be a K1. I mean, I can consider, of course, f of x. Let's call it like this: f of big variable x in K1 with big X. Right? I introduced this capital X because I want to distinguish it from this X that we have. I mean, so in K1X, an element in K1X, let's say I don't know, G, it means that you write it as rk small x times x to the k plus rk minus 1 x times x to the k minus 1, and so on. Okay? And the way to add two of these guys, I mean, if you have a g prime, say rk prime, yeah.
Sorry, this step is a bit unclear to me because now you're defining a polynomial with two variables, small x and big X. So for me, this is a bivariate polynomial, and like you're only putting one variable in J, the big X. And so I'm like kind of confused. How do you evaluate the small Rx coefficients now?
I mean, for me, the R coefficients are simply elements in a field.
Yes.
Okay? I mean, so this is what I wanted to say here. If you now want to multiply these two together, so in particular, you will have, you should have rk x times rk prime x times x, capital X, to the 2k.
Yes. Right. Okay.
Right?
You're just doing these as coefficients, and then you don't evaluate them. Just. Yeah.
But in fact, what I need to do here is the multiplication here. It needs to be multiplication mod f, because the way I multiply coefficients of polynomials is I multiply them in the field they came from. Right? So this needs to be multiplication mod f. So you multiply rk and rk prime, and then you do long division by the polynomial f. Is this clear? Of course, there are many other terms here. Okay, so this is, if you want, this is it's like a polynomial whose coefficients are polynomials modulo f. So, yeah.
Oh, modulo f just means divided by f, like long division by f polynomial.
Yes, I mean modulo f. If I want to do r1 times r2 modulo f, I write it. I mean, I am guaranteed that there is some polynomial q and polynomial r such that I have this equality, right? With r, I mean the degree of r is strictly smaller than the degree of f. It's like in integers, right?
Yeah, makes sense.
Okay, and then I throw away this part. I don't care. I just say r1, r2 is equal to r modulo f. Okay, so and this is what I do in K1. K1, remember, it was defined to be all polynomials of degree smaller than the degree of f, with addition and multiplication being modulo f. And we showed that this is a field. And since it is a field, now I can consider polynomials over this field. How these creatures behave. I mean, if you have two of them, say g and g prime, you do multiplication of polynomials, but when you need to multiply the coefficients, which are these rk prime and so on, you do the modulo f. Okay, is this clear? This is really like touching like a central point in this splitting fields. So now, okay, I can consider f with capital X in K1 of X. How can I do it? Because f had coefficient in Q, in the ground field. And of course, the ground field F, I mean Q, is simply a subset of these guys, right? I mean, so in particular, if you know, F had F was I mean, now I write F as x to the 4 minus 2. 2, I regard it as a constant polynomial. Let's call it R0. R0x, I call it 2. And now F is a polynomial over the field K1 with a new variable x, I mean capital X. But what I am guaranteed in K1 is that F has a root. Why? Yeah.
So, I mean, this means that independently of what primitive polynomial over what field you have, you can always find this F such that even if it's the most abstract thing in the world, you're guaranteed to find all of the roots needed for it to become a splitting field.
Yeah, this would be the eventual conclusion of our discussion, but let's kind of build it up.
Mm-hmm. Sure. Yeah, I agree.
So I first claim that in this setup, F has a root in K1. Now, how do you see it? I mean, remember what is K1? K1 is the remainder polynomials with modulo F arithmetic. In particular, in K1, I have the remainder polynomial, I mean, x, I mean, small x, let's call it maybe R1. We can call it R1. R1x being the polynomial x. And this is a legitimate element in K1 because the degree of R1 is 1, which is strictly smaller than the degree of F. Now I plug in this R1x, I plug it into F capital X. So the notation typically for substituting an element in a polynomial is like this, right? And when you have a polynomial, and I mean a polynomial over a field, and you substitute an element in this field into this polynomial, you get an element in the field. So this, I know without doing any computation, I know that the result must be an element in K1. Right? This is kind of the basic mechanics of a substitution. Okay, but now I really start to compute. I mean, it's not much. So it means that I get F with lowercase x. Right? This is what I mean, this is F of x, substitute x. So all I do is I replace the big variable x with the with the lowercase x. Yes.
I'm sorry. It may sound obvious, but I don't understand this. Why are you not replacing big X by R1 of X, not just X small x?
Well, I mean, R1 of x is defined. I just
Sorry. Yeah. Okay, it was obvious. Thank you.
okay. So I replace the. I mean, it's not like just a technical issue. It's like it's kind of a meta trick. Since I can substitute any polynomial with a variable small x, I mean, any polynomial of degree smaller than the degree of f, I substitute this degree 1 polynomial x. When I substitute x into f capital X, I get, of course, f lowercase x, which needs to be an element in the field K1. But in the field K1, I have modulo f arithmetic. So f with lower variable, I mean, lowercase x is 0 in K1, because in K1 I do modulo f. So this is all to say that f of capital X has a root in K1. One root, I mean, I don't know anything. I just have one root. Is this clear, Carlos?
It's clear. Like I agree with you 100%. It just feels like cheating, kind of. I mean, not cheating, but I don't know how to say it. Like, fair enough, I agree with what you said, but it's like you are making up this construction such that we can go this way. But I don't know. Yeah.
It's indeed an abstract construction, but nevertheless, it's you can follow every step and you see that it's true.
Yeah. Fair enough. I'm like Nicholas. Like, I understand now the proof. But yeah, sometimes these arguments are like, I don't know how to say it. They don't feel real though. I don't know.
No, it's true that it's kind of a meta trick. I mean, but that's the only way we can reason about because in Q itself, okay, I mean, the thing we are like studying a concrete example, so this could be made a bit more concrete. In our concrete example, we know what are the future roots of this polynomial, because we know how the behavior of these things happen in the complex numbers. But in general, you give me a field, you give me a prime polynomial, I don't know, I mean, if it doesn't have any root, the only thing I could, and I don't know how to include this field into some bigger field that I already know. I mean, then the only thing I could do is add kind of a new symbol that would be a root of this polynomial. Being a root of this polynomial, it means that this symbol satisfies a certain algebraic relation. Yes. And that's the only thing I can do abstractly. So and this construction, in fact, it does exactly that. It adds up a new symbol that is, I mean, is a root of the polynomial f. That means it satisfies the algebraic relation f of this element, f of alpha. Let's call it alpha. This is typically denoted just for like disambiguation. We denote it in kind of a different letter. So what I did here, okay, let me, I could even explain it slightly better with this formal construction of adding alpha. I mean, this is related to what we also discussed, that I could take a Q, let's say, and consider the min. I mean, I could take Q. I take F. In our case, F is x to the 4 minus 2, and say alpha is a root of F in some bigger field. I mean, if I knew that there is a bigger field, let's call it K. If I knew that there is a bigger field containing Q and containing a root of F, then I could consider the minimal field containing Q and containing alpha. How do I do it? I think that would have to wait after the break. But it turns out that to do Q of alpha, I mean to consider the minimal field containing Q and containing alpha is the same as doing K1. Okay, it's the same as doing, this is going to be isomorphic to simply do Q x modulo F.
Okay.
Okay, so what I did here is I simply added some abstract root of the polynomial in a minimal way. Yeah, but let's take a break, right? It's good to
Sure.
pause.
So at 11:13, we're here.
Yeah.
Okay. Cheers.
Okay. Can we continue?
Sure. As for the topic when we finish, there's also one question from Lisa on the chat. That we can address next.
Yeah, go ahead. With
Yeah. You told that we can assume that for the computer, two isomorphic objects are the same. Can you explain it, like why it is the same? I understood from your explanation that they are kind of the same size, the same structure, but I don't understand why they are the same.
Okay, so let's consider this this drawing of, say, a billion groups with an isomorphism F, right? Let's suppose G and H are a billion groups, and F is an isomorphism. I write the addition table of G, and then I apply F on the addition table of G. It means I apply F on all the elements in G, and I apply F on all the cells, right? All the blue cells. But I know two things. I mean, first of all, I know that F is a bijective map. That means that when I apply F on the elements of G, I get all the elements in H, right?
Yes.
I mean, it's a bijective. I not only that I get all the elements in H, I get it with no repetition. I mean, I had 3 elements in G. I apply a bijective map. I get 3 distinct elements in H, which are exhaustive. I mean, they comprise a full list of the element in H. In what order, I don't know, but it's a full list. Now I apply F on the cells. I mean, on G1 plus G1, for example. This, by definition, is F of G1 plus G1, but F is a homomorphism. So this is in fact equal to F of G1 plus F of G1. Whatever it is in H, I have no clue, but it must be F of G1 plus F of G1. So what I get when I apply F on the addition table of G, I get the full addition table of H.
I see. So the order might differ, but the elements will be the same.
Exactly. So I
okay, clear.
I get some representation of the addition table of H. Again, I don't know in what order. I mean, it could be that G3 would have been the unit element in G. So let's say 0G. And then I would know that since F is a homomorphism, I would know that F of G3, this guy, is in fact must be the 0 element in H, right? But a priori, I don't care. All I know is that I get a representation of the multiple table in H, and so from a computer point of view, it doesn't matter. I mean, whether you write the 0 element in the 3rd place or in the 4th place doesn't make a difference. Okay?
Clear. Thank you.
So, I mean, again, from a computer point of view, all you care is you have a bunch of symbols and you have an addition table, or I mean, you have a binary operation between these symbols, and you have a table of how to convert a binary operation of 2 symbols into a new symbol on the list. And the same goes for an isomorphism of fields, only that in an isomorphism of fields, you will identify both the addition table and the multiplication table. So again, from a computer point of view, 2 isomorphic fields, they are the same. I mean, you call the symbols in a different name. Okay, is this clear?
Yes.
This is why the notion of isomorphism is so important to us, because we cannot guarantee. I mean, we make constructions, especially with this splitting field is a very good example. We make a construction that introduces a new set of symbols. In this case, these remainder polynomials and so on. And possibly there could be another construction that does this. I mean, that has the same properties. And what we want to show is that these 2 constructions will result in isomorphic fields. So this is kind of one one use of this notion of isomorphism. But before the break, we spoke. I told you about an alternative way to interpret kx modulo f. We saw that kx modulo f contains a root of f, which just for clarity I denoted as alpha. But alpha is really this remainder polynomial x. Okay, thought of as in this field K1. Now, just for maybe like a slightly simpler example, suppose you had a gx being ex squared plus 1 as a polynomial over Q. As a polynomial over Q, it's prime because you don't have any rational number satisfying x squared plus 1 equals 0. So you don't have any root of these polynomials, and it's a polynomial of degree 2, so it must be prime. And now, suppose I didn't know, of course, a posteriori, since we already know about the complex numbers, we know what should be the roots. The root should be plus and minus I. But suppose I didn't know anything about the complex numbers, right? At some point in the history, it must have been the case. So what I do, I introduce a new symbol, alpha, and I would like to consider the minimal field containing Q and containing alpha, such that alpha satisfy a relation alpha squared plus 1 equals 0. So what do? I consider, and this, let me just find it in the notes, you can then follow better. Yeah, okay, so this is slightly before proposition 552. I consider alpha, Q alpha as the set of quotients let's call it okay, let's just for compatibility with the notes, let's denote this polynomial as phi. Okay, and now I consider Q alpha. So I want and I want to adjoin a new element alpha that will be a root of phi. A root of phi simply means it satisfies this algebraic relation, alpha squared plus 1 equals 0. And the way to do it, I consider all the quotients f alpha modulo g alpha, such that f and g are polynomials in the field Q, over the field, the ground field Q. And a G is not the zero polynomial. Now, what I mean, I claim that this is a field. So, of course, you can add two things together. And if you have a f of alpha modulo g of alpha, and you want to add to it a f prime of alpha, g prime of alpha, then you do what you know from elementary school. I mean, you do f alpha g prime alpha. Plus f prime alpha g of alpha divided by g alpha g prime alpha. And this is again a legitimate element in Q of alpha, because it's a quotient of two of two polynomials when you substitute alpha. And the the inverse of f of alpha modulo g of alpha, the multiplicative inverse, you simply invert the order. I mean, g of alpha modulo f of alpha. Of course, when you multiply these two together, you get 1. Yeah.
So you claim that this is a field, so Q of alpha, but so is it guaranteed because of how is it constructed, or what's the way to prove that this is indeed a field?
Okay, so to show that it is a field, I need to define addition and multiplication operations.
Exactly.
I need to have a 0 and 1, I mean, neutral elements with respect to addition and multiplication.
Mm-hmm.
And I need to have associativity and distributivity and also inverses.
Yeah. Okay.
So addition and multiplication I define here. I mean, this is addition. Multiplication, you can expect the same. I mean, if you want to multiply f alpha modulo g alpha with f prime alpha modulo g prime alpha, then you multiply f of alpha times f prime of alpha. If you want, you can regard it as you take the polynomial f, you multiply it as a polynomial with f prime, whatever it is, and you substitute alpha. And the same you do in the bottom. Right? I mean, f and g, remember, f and g are polynomials. Okay? So addition and multiplication I define. Of course, it's going to be associative because we know that addition and multiplication of polynomials are associative. And here I just do it in the nominator and the denominator. Yeah, is there a question?
Yeah, my question is about the definition of Q of alpha as well. You say it's the set Q adjoined with the alpha elements, but when you write concrete definition like this, I don't see there's a new element.
Well,
here.
I mean, you take the polynomial, fx equals x, and then in particular you would have f of alpha, which is simply alpha. I mean, maybe a better way to introduce it would be, how would you construct a minimal field containing Q and containing alpha that satisfy this purple relation? Well, so you introduce a symbol like alpha, and so alpha must be an element in this, whatever this field is, alpha must be an element in it. But since it is a field, I must have alpha square, alpha cube, and so on. They also have to be in this field, right? Because it's a field, it's closed under multiplication of 2. I mean, if alpha is in this field, then alpha times alpha must be in this field.
Yeah.
Okay? But also, if A is a rational number, then A times alpha also must be in Q of alpha.
Yeah.
And similarly, A times alpha square also. So all in all, for every polynomial f over the rational numbers, if I plug in alpha, f of alpha must be an element in Q of alpha.
Oh, I see. Okay.
Okay? Now, this is supposed to be a field. So alpha minus 1, there must be some kind of element that is the inverse of alpha. So alpha minus 1 must belong to Q of alpha. And similarly, alpha minus 2 and so on, they also must belong to Q of alpha.
Yep.
Okay, and of course, you take a rational number, A, then A times alpha minus 1 must be also in Q of alpha. And so, for any polynomial G, over Q, I must have 1 over G of alpha belonging to Q of alpha.
Yeah, makes a lot of sense. Thanks.
And of course, this means that, of course, G needs to be non-zero. G is non-zero. But since f of alpha and 1 over G of alpha are in Q of alpha, I must have that f of alpha modulo G of alpha is an element in Q of alpha. So far, I mean, assuming that Q of alpha exists, I kind of detected a necessary elements that must be in Q of alpha. And I claim that this collection of elements, I mean, namely, all the elements of the form F alpha modulo G alpha are a sufficient list of elements so that Q of alpha will be a field. Okay, so I mean, I assumed that Q of alpha exists, or I said if Q of alpha exists, it must contain all these elements of, all elements of this form. And now I show that the collection of all elements of this form actually constitute a field. Okay, so how do I show it? Well, I need to show you how to define addition and multiplication. This addition and multiplication are defined like this. And now I need to show you well, associativity of addition and associativity of multiplication, they follow from associativity and, I mean, of addition and multiplication of polynomials over Q, right? And the inverse, if I want the additive inverse of an element of this form, well, I have it. I mean, this is simply, you do, let's say you do minus on the numerator. Okay, and of course, this by the way we defined addition, the addition operation, if you do f of alpha modulo g of alpha, and you add to it minus f of alpha modulo g of alpha, you get the zero element. The zero element, by the way, you can represent, there are different ways to represent it, but you can take the zero polynomial. I mean, you take the zero polynomial modulo any guy that is non-zero. And if you want an inverse, like a multiplicative inverse, that's also, I mean, it's also very simple. You have f of alpha modulo g of alpha. You take an inverse. It's like a g of alpha modulo f of alpha. And what you want to remember, so all I said now is relevant for any abstract symbol alpha, right? I could actually introduce a new symbol alpha and consider this collection of all polynomials with with coefficients in Q, but with variable alpha, the variable, the new symbol, and this would indeed constitute a field. But in our case, we also want that alpha would satisfy this relation, this alpha squared plus 1 equals 0. So that's not a problem. What we do, I mean, in our case, we have phi x is x squared plus 1. And so when I have an alpha, of course, satisfy this relation. Alpha is a root of phi. So when I do f of alpha modulo g of alpha, I can, it's like, of course, it's like taking the polynomial fx and substituting alpha. But what I can do is first reduce f and g modulo phi. So I can always write f as say q1 phi plus r1, and g as q2 phi plus r2. And since alpha is a root of the polynomial phi, when I substitute alpha in f, I get a q1 of alpha, phi of alpha, plus r1 of alpha. But phi of alpha is 0, right? So I get that f of alpha is r1 of alpha, where r1 is the reduction of f modulo phi. Okay, and the same would be true for g of alpha would be r2 of alpha. So in fact, when I consider f of alpha modulo g of alpha in this setup, it is equal, simply equal to R1 alpha modulo R2 of alpha, where R1 and R2 are the mod phi reduction of f and g. Okay, so in fact, I could rewrite Q of alpha as the set of all R1 alpha modulo R2 of alpha, as such that R1 and R2 are polynomials over Q, with R2 not the zero polynomial, and the degree of R1 and the degree of R2 are strictly smaller than the degree of phi, which in this case is 2. Okay? And that's it. It's a field. We showed that it's a field. The relation alpha square plus 1 equals 0 is being taken into account by this consideration. I mean, this relation would not happen if alpha would be some kind of abstract new variable, but if it's an abstract variable satisfying this relation, then I have this equality in Q of alpha. Yes.
So we can define any Q of alpha on any phi of x as long as the degree of phi of x is less than f or g. I mean, my question basically is like we wrote alpha square plus 1 equals 0, but we could have very well written like alpha square plus 2 equals 0, alpha square plus 3, and anything, right? We don't know the roots of these things, but we just define the Q of alpha like this, so we know that in this field Q of alpha there's going to be a root.
Yes, of course. If alpha was already a root in the original field, then you don't add anything. I mean,
yes, yeah.
Because again, Q of alpha, you should think of it as like the minimal field containing Q and alpha. So if alpha was, and this by the consideration we talked about, that's the way to construct it. So of course, if alpha was already in Q, then you don't get anything new. But alpha could be a symbol satisfying any polynomial relation, being a root of any polynomial, again over Q. Now we know, so remember this phi was x squared plus 1. We know, because we know the complex numbers, we know that the roots of this polynomial are I and minus I. Which one of these is alpha? I don't know, and I don't care. I mean, in fact, so Q of alpha would be isomorphic to what is called the Gaussian rationals. It's, I mean, one way to view it is all the numbers of the form a plus bi, such that a and b are rationals. But of course, you could write it as all the numbers of the form a plus, I mean, a minus bi, or a plus b times minus I, where a and b are rationals. These two fields are isomorphic, right? So which one of these is alpha, I don't know, because alpha was simply an abstract symbol satisfying a relation. But the result I get is the same. Okay? Yeah.
So then also, since the constructions are like this abstract, that's why you never have only some of the roots, and you always can have all of them, basically, because you know them beforehand, so you can always construct some kind of abstract symbol such that you can clean up all of the roots of your polynomial, right?
Well, so it not quite. I mean, because in the general setup, I don't know what are the roots in advance. I mean, I don't have this. I mean, in our case, we had these complex numbers in which we can find all the roots.
Yeah, or the square root of 2, but you just made up a symbol such that you can carry over the computation. No?
Yeah, but the thing is, like, let's we go back to the example of a phi x equals x4 plus what is it, plus 2 or minus 2? I think let's see, minus 2. Okay, so over Q, of course. And now and I didn't say, but this Q of alpha is isomorphic to just take polynomials over Q and mod out by the prime polynomial phi. Why? Because this specific blue description of Q of alpha, it tells you that it's the same as doing polynomials modulo phi. Because what did you do in polynomials modulo phi? You had this guy, you had remainder polynomials, right? R, it's like the set of all remainder polynomials with addition and multiplication modulo phi. But of course, if you have R1 and R2, since in this guy, in K1, let me, you know what, let me write it in a different place just to have more room. So we have, on one hand, we have what we called K1. This was a Q of X modulo phi. Phi could be whatever prime polynomial you want. And this was all the remainder polynomials R. So the degree of R is smaller than the degree of phi. And on the other hand, we have Q of alpha. But we took a description of Q of alpha as all the quotients R1 alpha modulo R2 of alpha, such that basically the degree of R1 and the degree of R2 are smaller than the degree of phi. Now, I claim that these two fields, we showed each separately, we showed that each of these sets is a field. But I claim they are isomorphic fields. I mean, I can construct the isomorphism and show it kind of formally, but to get the intuition, I mean, what you have here, if you have R1 and R2 in K1, then of course, because, sorry, this is K1. Because K1 is a field, I have R2 of K, I mean, R2 inverse. Right? This is, we call it, just to be more compatible with the notation, this is R1x and R2x. But remember that x is a root of phi. Right? It was a root of phi when I consider phi capital X in K1 capital X. But this is just to say that X is a root of phi. But X, we called it alpha. Right?
Yeah.
And indeed, it sat in K1, X satisfies phi of X, let's say, or maybe alpha. Alpha satisfies. Alpha satisfies alpha to the 4 minus 2 equal to 0. Because this is simply saying x to the 4 minus 2 equal to 0. And this is exactly phi of x, lowercase x. And in K1, phi of lowercase x, I mean, in K1, you do modulo phi. K1 is with addition modulo phi and multiplication modulo phi. Is this clear? This
yeah, it is. Indeed, I kind of get the intuition that if you find a splitting field over another field, you can always find a splitting field over the splitting field, and so on and so forth. So it just never ends.
Well, I will get to it soon, but first I want you to understand this this first step.
Yes, for me at least, this is understood.
So what I'm doing here, I mean, the K1 is like adjoining a new element alpha, satisfying a new element alpha, satisfying a relation alpha to the 4 minus 2 equals 0, and doing it in a minimal way because it's the same as doing Q of alpha. And we basically reasoned about the construction of Q of alpha. It's the minimal thing that you can do if you want to introduce a new symbol, alpha satisfying the relation phi of alpha equals 0. So what happened is, I mean, again, we take this example of x to the 4 minus 2. Now I took qx modulo phi, And I know that phi has a root. This is isomorphic to Q alpha for alpha satisfying alpha to the 4 minus 2 equals 0. Which, so, I mean, this alpha, I mean, we know a posteriori that alpha is either a plus minus square, sorry, a fourth root of 2, or a plus minus I times a fourth root of 2. This, but this I put in brackets because we don't care, we don't know. For us, alpha is just a symbol. I mean, a symbol satisfying a relation. So, and now I consider, so we know that phi x, this is K1. Now phi capital X is in K1 capital X. And we know that this is, it has a root alpha. So it is X minus alpha times some phi prime. And of course, the degree of phi prime must be smaller than the degree, I mean, than the degree of phi. It's in fact exactly 1 degree less than phi. Okay, and now I consider K2. K2, okay, so before I consider it, I mean, now if phi prime has linear factors, or maybe I could write it like this. Say phi prime is of X is some linear factors X minus alpha I equals 1 up to some S times some, this is phi prime, some phi double prime, where phi double prime is well, it doesn't have to be, this needs to be phi double prime. It doesn't have to be prime. Okay, so let's say it like this. Let phi double prime X equals P1 of X up to PS of X, where P1 up to PS are prime over K1 of X. I mean, over K1, or prime in K1 of X. Okay, some of them may be linear.
But aren't you missing a prime in the phi of big X? Yeah.
So some of them may be linear. It means that I drop them. I mean, without loss of generality, suppose P pi of x is not linear for every I bigger than some index in the middle. I mean, some j. Then I take each of these guys. I can consider k1x modulo p j plus 1 of x. This I call k2. And by the construction that that we get, I mean, now I have a root. There exists alpha 2, a root of pj plus 1 of x in k2. Right? This is the construction. This k2, it needs to be isomorphic to k1, join some alpha 2. Yeah.
So this arises two questions to me. The first one is there any direct relation between alpha 2 and alpha 1? Is alpha 2 like some subgroup, or I don't know, whatever you want to call it, of alpha 1? Like a subgroup of roots or something like this?
I mean, alpha 2 and alpha 1 are both going to be roots of the polynomial phi. But there are going to be roots, there are going to be different roots, because when I considered now phi double, actually here it should be phi, no, it should be phi prime, not phi double prime. I mean, I took out the root alpha from phi, and I'm left with phi prime. And now I decompose phi prime into prime factors. Mm-hmm. Some of them may be linear, so some of them may be like x minus alpha I. Okay, so it could be that k1 of x. I mean, in k1 of x, phi has more than one root. I mean, just as in the example of when you add the symbol I, then you get two roots of the polynomial x squared plus 1. But I don't care. I mean, I just take whatever I'm left with. I mean, let's say pi of x for I bigger than j are the nonlinear factors of phi prime. I take one of them. I choose whatever. You start with the first one, and you take the modulo. I mean, the modulo field of k1 of x with respect to this polynomial. This is a new field, k2, because I modded out by a prime polynomial. I get a field again, and this field contains a root alpha 2 of this polynomial pj plus 1.
That makes sense. So,
okay, and of course, since I mean, pj plus 1 is simply a prime factor of phi, then this root alpha 2 is also going to be a root of phi. And I continue indefinite. I mean, I continue until I run out. Basically, in every step, I reduce the degree, and the degree is finite. So I know that at some finite I mean, this process terminates. Now, what happens in this, I mean, in this example, I take a phi is, again, is like x to the 4 minus 2. I take qx modulo phi. This is some q alpha, for alpha being a root of this polynomial. Which one, I don't know. But let's say this is q to the square root, sorry, fourth root of 2, which you can describe as a plus b fourth root of 2, where a and b are rationals. Right? You know how to add and multiply. You simply introduced a new symbol and it satisfies a certain relation. Of course, since you introduced it, a square root of 2, which was not an original element in Q, will suddenly, I mean, must be an element in this extension, because square root of 2 is fourth root of 2 times fourth root of 2. So it must be an element in Q of fourth root of 2. Okay, so you are doing some additional stuff when you add a root. But now, okay, so now I added this root. Now I look at the polynomial phi. I'm not going to write this big variable. I think you got the point. But now x to the 4 minus 2 can be written as x minus fourth root of 2 times x plus fourth root of 2 times, if you do the long division, you check what is left, you get x squared plus square root of 2. And x squared plus square root of 2 does not have any root. So in Q, square root of 2, x, this guy, which we can call phi prime, phi prime does not have any root, because in order for phi prime to have a root in this guy, I would need some symbol like I mean, I would need some symbol satisfying the symbol square equals to -1.
Yep. I see.
Okay, so now I continue the process and I do q square root, sorry, a fourth root of 2 polynomials modulo phi prime. Okay, and now I am guaranteed to get a root of phi prime. What is this root? I mean, again, a posteriori we have the complex number and so on, but a priori it would be just a new symbol satisfying the relation x squared plus square root of 2 equals 0. But in practice, what I get is now I have q of fourth root of 2, and let's say I times fourth root of 2. Right? Because this is like the roots of this guy are plus minus I fourth root of 2. Okay, so how do you write it? I mean, this guy is like all the elements of the form A plus B fourth root of 2 plus C times I fourth root of 2, where A, B, and C are elements in Q. Okay, and this is a splitting field. This splits the polynomial phi completely, right? Once I have I fourth root of 2, I have also minus I fourth root of 2, and I have exactly 4 roots of the polynomial phi. We can even simplify a bit. This is going to be isomorphic to simply take a Q and adjoin fourth root of 2 and also adjoin I. If you take multiplication of all these guys, you get, I mean, this by definition is like all the elements of the form A plus A plus B fourth root of 2 plus CI. Okay? Yeah.
Would there be a way to get this field just by adding one extra element?
No.
And
Well, sorry. Actually, the answer is yes. But this is another proposition that I don't want to get into. Yeah, there is a way.
okay, thanks.
But for us, is like we do an iterative process. We add roots to whatever prime factors of the original polynomial that we are left with. And eventually, we know that eventually the process has to terminate because we reduce the degree every time. And so we are left with a splitting field for the polynomial phi. And we had a proposition that said that a splitting field is unique up to isomorphism. Because if you think of it, of course, I took phi of, I took a phi in Q of X, I modded out, I added some abstract element alpha that is a root of this polynomial. Is this alpha fourth root of 2, or is it I times fourth root of 2? I don't know. So all I can guarantee is that eventually I get some the eventual field, a splitting field is unique up to isomorphism. But I cannot control in the process. I don't know what root did I add at any point. Okay, so this is we are a bit over time, but I want this point to be clear. So any other questions on this issue?
My second one was whether this was diverging or converging, but since you removed degree, it has to converge at some point to a single element. It's all for me. Thank you very much, by the way, Matan. This was really, really useful.
Okay, yeah, I'm glad this is and now just to finish up, I mean, what do? We consider over FP, we consider the polynomial x to the q minus x, where q is the power of p. Okay, this is phi. And so I get a splitting field unique up to isomorphism of this guy. And this is called FQ. So it contains FP. And in this guy, so this polynomial, there is a consideration that shows that all the roots of this polynomial must be different. It cannot have repeated roots. Okay, so I see that people are leaving. So let's just continue next time with whatever other questions you have. But try to go over the notes and see if you have any gaps.
Thank you very much.
Okay.
Thank you so much.
Thank you.
Thank you.
See you next week.
Bye-bye.
Bye-bye.